Hello, everyone. Welcome to Lecture 2. Today we will be talking about vectors, um, which is Chapter 1, the remainder of Chapter 1 in the book. All right, so last time, as you may remember, we talked about physical objects, physical quantities, um, which were objects with a number and a unit. The proper name for that type of object is a scalar. So a number plus a unit is often called a scalar. Unfortunately, we don't live in a one-dimensional world where everything is just mass and meters. We live in a three-dimensional world, or for those of you who go on to relativity, a four-dimensional world. So we have x, y, and z. And in general, we will have to specify not only distance, but also direction. So the way we can do that, of course, is through vectors. And so vectors are objects that have a magnitude, how long they are, or how far they are, or how large a force is, and a direction. So if I push on you in this direction, that's a magnitude, how much force, and a direction. Now, we're going to denote this different ways throughout the class. Sometimes I will denote it with a bold symbol. That's how it's done in the book. Sometimes I will do that with a little vector symbol on top. And sometimes it'll be a combination of these. Regardless, they all mean the same thing. They mean an object with a magnitude and a direction. And the key thing is that vectors can be represented by an arrow. So the arrow, obviously the direction, signifies the direction of the vector, and the length of that vector is its magnitude. So that's how we're going to start off. We're going to start off by thinking of vectors just pictorially as arrows sitting in space. And so the first property of vectors you need to know is that when I talk about something as a vector, rather than a point in space, it's intended to be kind of abstract. So this pencil thing is a vector. It doesn't matter whether it's here or here or here. It's always the same vector. It's always the same length and direction. So it doesn't matter where the vector starts and ends. All that matters is the magnitude and direction. Another property of vectors is that if I add a negative sign to the vector, I'm just flipping its direction. So you'll notice that I start at the tail of the vector and draw a line to the head of the vector. That's my arrow. When I add a negative sign, I start at the other end and I go backwards. Okay, so there are a couple of properties of vectors. Some definitions: the length of a vector is called its magnitude. And keep in mind, when I say the length of the vector, I just mean how big it is. So that can have units of distance. The length of this guy is, let's say, 12 centimeters. The length of a force vector is going to have some units. In that case, we'll learn newtons is going to be its unit. So the magnitude doesn't have to have units of distance, but it is telling you how big a vector is. There are two different ways we will denote this. One is that we will put absolute value signs around the vector, or occasionally we will simply drop the bold or drop that vector symbol. So if I write just the letter without anything else, that will be the length of the vector, the magnitude of the vector. So if you think about it, magnitude is a number with units, the same units as the vector itself. So that's a scalar. Magnitude of a vector is a scalar. So I want to keep reminding you of this. Vectors are quantities with units, but just like scalars, they can have any units they want. If I push on something with a force in that direction, the direction is that, and the force has units of newtons. Gravity is going to have units of meters per second squared downward. So the units can be anything, not just distance. So let's take an example of this. Imagine I have a plane that's flying 200 meters per second due north. What's the magnitude of this velocity vector? So the velocity vector is an object with a magnitude and a direction. The direction is due north. The magnitude is just the length of that vector, 200 meters per second. Okay. So there are various different ways that we can specify vectors. The direction, for example, I can specify in various different ways. For example, what I just said, 200 meters per second going north, that's called the heading. It's like what you would do if you were an airline pilot. So I could say 15 meters due northeast. that would specify the direction of a vector. Of course, for our purposes, we usually want to put a little bit more math behind these things. We're going to use angles. So the more conventional way that we will do it is we will draw out a vector, we will draw out a direction via some angle that it makes with some fixed axis. So here, for example, the same vector would have a magnitude of 15 meters and a direction 45 degrees north of east. So if this guy is east and pointing up is north, then theta is going to be 45 degrees north of east. And as you'll see throughout these lectures, we're going to use that more of the time. All right, so what can we do with vectors? Well, we can represent the vector by an arrow or a magnitude in a direction. We can add, subtract, multiply vectors, all fairly straightforward. Let's start by talking about adding vectors. I want to add two vectors. The way I'm going to do that is pretty straightforward. I will simply take the first vector, let's call it A. I'll lay it out. And apologies in advance if there's any background noise. Then I'll take the second vector, let's say B. So let's say B is a vector that points to the right with this magnitude. And what I'll do is I'll simply put it just at the end of A. So it's head of A to tail of B. And the result, starting from the beginning and going here, is their sum, A plus B. So you place them back to back, head to tail. That's how you add vectors. So let's take a really simple example of this. Let's say I wanted you to add A plus negative A. How would we do this? Well, we'd start out, we'd place A right here, and then I'd want to add negative A. So remember, negative A is just A flipped around. You start from the top and go to the bottom instead of the other way around. So A plus negative A just comes back to where you started. The net result is 0. So that's the 0 vector. It doesn't go anywhere. All right. So just like regular addition, it doesn't matter in which order we add vectors. It's commutative. So A plus B is equal to B plus A. You can see that here. If I first put down B, then put down A, the results, this blue vector, is the same. Now, a quick question I want you to think for a quick second. Does that mean that the magnitude of C is equal to the magnitude of A plus the magnitude of B? So is the magnitude of A plus B equal to the magnitude of A plus the magnitude of B? The answer is no. They will always be less than or equal to the sum of the magnitudes. And the reason for this is, well, for example, here C is shorter than A plus B in magnitude because they're not parallel to each other. So the only case where they're exactly equal to each other, the magnitudes are equal to the sum of the magnitudes, is if they are parallel to each other. So I just want to remind you of this. Adding vectors is not the same as adding scalars. It will not be the case that their magnitudes add up in this way. Okie dokie. So subtracting vectors, that's actually pretty much what we just saw. So to subtract a vector, the easiest way to do that is simply say that A minus B is the same thing as A plus negative B. So we know how to draw A, we know how to draw negative B, and then we just add the negative vector. So for example here, if A points up and to the right, B points down and to the right. Give it 1 second to appear on the screen. Apologies for the lag. There we go. So A minus B is equal to A plus negative B. So that's just B flipped around, pointing up and to the left. You add them head to tail, exactly as we just learned, and here's the result, A minus B. So you add head to tail, you subtract head to tail after flipping it around. And so that's how we're going to work with vectors when we think of them as arrows. In practice, that's very rarely what we're going to do after this first lecture. The majority of the time, we're going to want to think of vectors in a certain coordinate system. So the way we're going to do this is introducing what are called vector components. The idea is as follows. Imagine I have some vector A that I'm interested in. And what I'm going to do is I'm going to write down some world that it lives in, some basis, a coordinate system. So here, for example, I've introduced the x and the y coordinates. And what you notice is that I can always take any vector A and I can always break it up into some thing that only points in the x direction, which I've labeled A sub x here, plus something that only points in the y direction, which is labeled AY here. So you'll notice these two are the same vector. So I can always break any vector up into x and y components. These are called the component vectors. And if it's a three-dimensional vector, of course, I'll have to use x, y, and z components. So I can always write the vector as a sum of component vectors that point along the two axes. A slightly more useful way to do this is to write what are called the component indices or the coordinates. Sorry, I'm skipping through this a little bit. So if I do the following, then you can just think of the head of the vector as some point in space with an x component and a y component. So like a coordinate, the way we usually think about points in space. That is another way of writing the vector. I write down the x and the y components. And that's going to allow us, for example, to very easily convert into a magnitude and an angle, magnitude A, angle theta, as drawn here, because I just do a little bit of trig. So let's go ahead and derive these formulas really quickly. We're going to do this 1,000 times in this class, so you'll get very, very comfortable with this. But I'm going to take my vector A, I'm going to break it up into an x and a y component, ax comma ay. And let's take a look at this. So the magnitude of ax is this, this side of the rectangle, of the triangle, the bottom side. That's adjacent to the angle theta. So ax over the magnitude of A, which is the hypotenuse of this triangle, is the adjacent over the hypotenuse. So here you have to remember your trig. You might have learned it as SOHCAHTOA, S-O-C-S-O-H-C-O-A-T-O-A. So adjacent over hypotenuse, that's ka, H, cosine adjacent over hypotenuse. This is cosine of the angle theta. Ax over A is cosine of the angle theta. If I multiply both sides by A, Ax is equal to A cosine theta. So sine of theta is equal to opposite over hypotenuse, and you can very easily convince yourself that that's the magnitude of ay. So for this particular vector I've shown, the x component is a cosine of theta, and the y component is a sine theta. So when I break the vector up into components, I'm going to be able to do things very nicely with trig, and it's going to make the math a lot easier. All right, so we can think of vectors as arrows. Sometimes that's useful, but not so often. The best way to do it is to immediately write down the components of the vector. The x, introduce a coordinate axis, right? Determine the x component and the y component using trigonometry and the information given. So once you do that, life is going to become much easier. For example, addition and subtraction, which were kind of a pain in the butt with arrows, those are now trivial. If D is A plus B, then you just add up the components. The x component of D is just the x component of A plus the x component of B. The y component of D is just the y component of A plus the y component of B. And similarly for subtraction. AX minus BX, AY minus BY are the components of the difference. The magnitude of a vector is just given by the Pythagorean theorem, right? We remember if we have a right triangle with lengths ax and ay, the hypotenuse, a squared, is equal to ax squared plus ay squared. If I had a three-dimensional version of this, there's a slight generalization of this, which would say plus az squared. So if I take the square root of that, the magnitude of a vector is the square root of ax squared plus ay squared plus az squared. And the angle, again, I could get from trigonometry. The tangent is opposite ay over adjacent ax, so theta is the inverse tangent of ay over ax. And here I want you to be a little careful. These formulas, particularly this angle formula, are only true for the vector labeled the way it was, where ax is this part and ay is that part. If I label a different angle, it's going to be a different formula. So do be careful about that. But the trig is going to be a lot nicer when I start to work in terms of components. The other thing that I want to emphasize now, it's going to come back quite a bit throughout the course of the class, is that these formulas, the fact that I can simply add or subtract the components independently, means that the x, y, and z components of the vector will basically behave independently. So I just work with x, solve that problem, work with y, solve that problem, work with z, solve that problem. That will be really nice because, for example, if I throw my pen and watch it fall, the x motion and the y motion will be completely separate. They will not talk to each other at all, and that's going to make the problem much, much easier to solve. So keep in mind that for a lot of problems, you're going to be able to work with each individual component separate. All right, so vector components make life a lot easier. Always write things in components. There's another way of doing this, which we won't use as much. I'm going to mention it because it is used in the textbook throughout the class. So another way of doing this, which is kind of the physicist's preferred way, is to use something known as unit vectors. A unit vector is a vector that just tells you about direction and not magnitude. So it's a vector that has a direction and it has a magnitude equal to 1. So for example, if I have a vector that's pointing along the x direction, the magnitude of that vector is 1, we call that I hat. If there's one pointing along the y direction, we call that j hat. Why they call that I hat and j hat instead of x hat and y hat, you got me. But that is the notation that is used historically. It comes from something known as quaternions, and those of you who go on to do virtual reality, it turns out any visualization software, they use the same notation. And it's actually a very, very common thing there. But for our purposes, I hat is the unit vector in the x direction. J hat is the unit vector in the y direction. K hat is the unit vector in the z direction. The important thing is these just specify direction. They don't specify magnitude. Oh, there it is again. So just the reason I say this is there are 3 different ways of writing the same vector, and we really do need to be able to go back and forth between them. Give it just a second here to appear. So option 1 was the first thing I told you. You can always just draw the vector. Write it as an arrow with some magnitude, some direction. That arrow specifies everything, of course, that you would need to know. The other option, my preferred option, is to write it in terms of components, ax, ay, and az. You should just think of that as the components of the head of the vector. The coordinates in the coordinate system. You would write that often as an ordered list, ax, comma, ay, comma, az. And then finally, if I really want to be a physicist about it, I would write it in terms of these unit vectors. A vector is ax times I hat plus ay times j hat plus az times k hat. And you can convince yourself that that gives, when I add these guys up pictorially, it gives me the same point in space as the. But far and away, the most common thing I will do is write it as an ordered list in terms of components. All right, so that is how we define vectors, how we add vectors, how we subtract vectors, and how we take their magnitudes and directions, which is a bit of trick. The last thing that we'll talk about in terms of how to manipulate vectors is multiplication. So there are actually many different ways to multiply vectors together. You can multiply two vectors together to get a scalar. You can multiply them to get a vector. You can actually multiply them together to get a matrix. That's something known as an outer product. But for us, the two we're going to care about is the dot product, which is combining two vectors to create a scalar, a single number, and the cross product, which combines two vectors to give you back a second vector, third vector. All right, so let's start with the dot product. The dot product is defined as follows. If I have a vector A, a vector V, A dot B, notice I draw a little dot multiplication here, is equal to the magnitude of A times the magnitude of B times the cosine of the angle phi in between them. Let me be very clear, this is not any phi in the problem. This is the angle between the vectors. Dot product of A and B is the magnitude of A times the magnitude of B times the cosine of the angle between them. Now it turns out there's another nice way of writing this, which is why sometimes components are very nice. I can also write this as AX times BX plus AY times BY plus AZ times DZ. You just add up the products of the components. So depending on what you're given in the problem, you'll either use this angle identity or you will use the Cartesian representation. All right, so what do we know about this object? The dot product is AB cos theta. Where is cosine of theta large? Sorry, cosine of phi large. This is the Greek letter phi for those who aren't familiar with it. And you will gradually get used to Greek letters in this class if you aren't already familiar with it. Maybe I should mention this guy up here is the Greek letter theta. All right, so the dot product is large when vectors are in the same direction. Cosine of phi looks like this. Starts off at 1, it goes through 0 at 90 degrees, or pi over 2 radians, and it goes to -1 when it hits 180 degrees. So if I want the maximal possible value of the dot product, I should pick phi equal to 0. The vector is pointing along the same direction. So if A dot B is equal to A times B, are those vectors parallel or perpendicular? This will appear in a second here. So think about that. If A dot B is equal to A times B, are the vectors parallel or perpendicular? Everyone try to write down an answer. It's useful if while these lectures are going, you actually try to write down an answer. Test your knowledge, because if you're finding that you're not understanding the questions as we go, we'll revisit them in the in-class section, and this is a good opportunity. So, parallel or perpendicular, the answer is parallel. So that's what I just discussed. If phi is equal to 0, that means the vectors are parallel and their dot product is just equal to the product of their magnitudes. How about if A dot B is equal to 0? Are those vectors parallel or perpendicular? Should be pretty obvious from the way I've stated the question, but in case you didn't get it, the answer is perpendicular. And here again, let's just take a look at the formula. If the dot product is 0, that means cosine of phi is 0. Phi is 90 degrees. That means that those vectors are perpendicular to each other. So there we go. All right, so that's the dot product. Now let's talk about the cross product. The cross product is kind of the opposite of the dot product. The dot product tells me how similar two vectors are, how much they are aligned with each other. The cross product tells us the opposite, how different two vectors are. So the cross product of two vectors gives me back another vector. The magnitude of that vector, the magnitude of the cross product, is simply A times B times now sine of the angle between them, sine of phi. So now cross product is going to be large when the vectors are perpendicular. Let's test this out. Let's say I were to tell you that the magnitude of the cross product, magnitude of A cross B, is equal to the magnitude of A times the magnitude of B. So does that mean that A and B are parallel or perpendicular? Think for a second. The answer is perpendicular. Apologies, not quite aligned, but if the two vectors are perpendicular to each other, that cross product is going to be large. If the cross product is 0, what does that mean? Well, it means that the vectors are parallel to each other. Two parallel vectors have a cross product that's equal to 0 because sine of 0 degrees is 0. Or anti-parallel. This would also be a 0 cross product. It's called anti-parallel when they point in exactly opposite directions. All right. So that's the magnitude of the cross product. There's one other thing we need, which is the direction of the cross product. And that's something we're going to get via a procedure known as the right-hand rule. So everyone try to do this with me. The right-hand rule goes as follows. Step 1, point your fingers along the direction of the first vector. So here I have A cross B. Take your right hand. That part should have been obvious, but here we go, right-hand rule. Point your fingers in the direction of the A vector. That's what it looks like for me, but obviously with the mirrored screens, it might look opposite for you. Next step, curl your fingers in the direction of the second vector, B. And your thumb should now point in the direction of the cross product. Point your fingers along A, curl your fingers along B, and point your thumb along the direction of the cross product. So that is the right-hand rule as I teach it and as I was taught it. Some people, there's slightly different ways. You can use your index finger for one, your middle finger for the other, and your thumb. That's another way of doing it. There are various ways you can do it. I prefer this version, but they should all give the same answer if you pick a good right-hand rule. And so that is the cross product. Magnitude is AB sine theta. Direction is given by the right-hand rule. So that is all the content that we have on vectors. As a quick summary, the reminder, we can draw vectors as arrows. We add and subtract by putting them back to back, head to tail, or head to head for subtraction. The easiest way to work with them, and far and away the most common thing we will do, is we will introduce components. So for example, we add A plus B by just adding AX plus BX and AY plus BY. And the thing that we're going to get a lot of practice on in class is converting between these two, a geometric representation of the vector and a numerical representation with these components by basically doing tricks. So remember that SOHCAHTOA. It's going to be your friend throughout this class. When you do need to multiply vectors, there are a couple of different options. The dot product, which is basically how similar two vectors are, how parallel they are. That'll be AB cosine theta, or phi, where phi is the angle between the vectors, and the cross product, which tells you how different they are, AB sine theta. And we will get the direction of that from the right hand. So that is all the content you will need for this. In class, we're going to do a lot of examples, practicing adding, pictorially, in terms of components, doing all that trig. I'd say the thing that you want to get the most practice on is really all this trig, because we'll use that throughout the class. And then we'll get a couple of practice problems on dot products and cross products. So thank you for listening to this lecture. I will see everyone in class. Have a nice rest of your day.